Okay, so on 3.3, what do we want to talk about? We gotta move, because we got a lot to do in this next one. You're not sitting back and can get the job done today.
6 and 7.
4 statistical measures that are invariant. In other words, they don't vary under a translation.
I got standard deviation, variance, IQR, and range.
Right, they don't change, do they?
Right.
They don't go anywhere, because they're measures of spread. So whether your spread is here, or you slide it over there, the measure of spread is still the same.
Okay.
Is that okay?
Right.
That quick of a,
That's reasonable.
all right, next answer to a question.
7.
Set of data is translated. Find the missing values. Well, we gotta figure out, if the median moves, does the median move?
Yes.
Good, because that's a measure of central tendency. So all your central tendencies move the same in the translation. So that measure of central tendency moved by what, 10 and a half?
Mm-hmm.
So what else moves by 10 and a half? Or wait, oh wait, no, hold up. If you thought of a box and whisker plot, there's the median, right? Okay, so it moved how? The median moved from, it moved back. It moved back 10 and a half. Okay, so the max and the min will move back 10 and a half. The interquartile range is gonna stay the same. Is that on there, the IQR? The range,
It's 12.
the range itself is gonna stay the same. Yeah, the same range is gonna happen, because all you're doing is sliding it. The standard deviation is gonna remain the same. The number of cases is gonna remain the same, right? The mean is gonna change, though. The mean is going to get smaller, isn't it?
It's
Or wait,
gonna
wait.
change by 10 and a half too, isn't
It will
It's
have,
gonna change by 10 and a half
Yeah.
times 10. Divided by,
it? Why would it do that?
why do you have to multiply and divide?
oh no, alright.
You see, if, for example, 1, 2, and 3 has a mean of 2, right? So now let's shift all of this over and call it 5, 6, and 7. We shifted it from here to here, we shifted it how far? 4. So we did a shift to 4, so what happened to the mean?
Increased by 4.
It also shifts by 4. So we slid that data there by 10 and a half. The mean is also going to slide by 10 and a half. Okay, next question. Is that it?
I didn't get all the way through it.
Okay.
I got to 11. So that was
You got 5 days to do this.
yeah, I forgot that it was assigned. I checked the whatchamacallit,
Assignments.
the assignment sheet, and it already moved back, and I didn't.
Well, all you gotta do is go to the top and, oh, I don't see what I'm looking for. Click, go back, look. Come on, we can't. This is supposed to be practice for college. Something like that, right? All right, here we are. Symmetries of graphs. The graph symmetry, when we talk about graph symmetry, we're talking about lines of reflection, because that's what's gonna show us symmetry. So there's all kinds of lines of reflection. You know, you can reflect over the y equals x line, and then you have an inverse. You can flip something over the x-axis, reflect it down or up. You can reflect it left and right over the y-axis. Now, what we've looked at in the past with you guys is, we've looked at what happens with graphs. And what we need to do is we need to take that a step further and see how we can prove what does and doesn't happen algebraically. That's the big part of this lesson. The big takeaway has got to be able to be how I prove a function is either what we call an odd or an even function, or it's neither. That's real important. Please, you gotta be really nice to these things. They'll just wear out the joints of the wood if you have your feet like that. And sorry, you don't want me to give you one of the black chairs, do you? You get the comfy, cozy chairs. We want to use those. So, we need, I think we can fit this. We can fit this on here. All you need to do is get a, like, -6 to 6. So
Oh, that's on the y-axis.
you need an X and a Y axis. And you need to be able to go 6 in each direction. So, I don't know if it's called activity 1 or it's called activity 1. And there's 2? Oh yeah, that's right, there's 2. Okay, so we need to copy the diagram, we need to draw the other half of the graph, so the result is point symmetric about the origin. So if it's point symmetric about the origin, that means that we need to go around the origin. We need to label this half A. So start with what you have here. And I have a brand new box of colored pencils. Yeah. So if you want to make your 4 lines 4 different colors, that'd be all styling. I gave you one when you were in geometry.
I took it out to use it to draw for my cuckoo's nest final. I'm doing a comic. And I forgot to put it back.
You're gonna have to get the plastic off. Can't do that. Stop watching. These are messed up. They're kind of weird in the end, aren't they? His ears?
Oh, yeah.
How messed up is yours?
It's just the thickness of it, it's just kind of odd at one end, the other end's
That's
fine.
that curve. Yeah, I got some from them that the corners were all disformed. Whatever. Yeah. Does it not work or what? You send mine in. Yeah, so if you get the bend in that right, and then get the end. And then draw your lines, really good. It might be of advantage to label the end of that line.
This is activity 1, right?
Yeah.
So you're seeing that it intersects at 6 planes?
Yeah.
Okay.
Intersection 6.
Activity 1.
What we, oh.
So you gotta send it over the origin for your first one. Are we square with that?
The y-axis.
No, over both. So when it says with respect to the origin, that means it needs to either rotate about the origin, you can think of it that way, or it needs to reflect over both the x and the y axis. I think that might be a better way of thinking of it.
Line A or for
Are
figure A.
you talking about step 3?
Step 1, I'm sorry.
Oh, symmetric around the origins using the diagonally adjacent quadrant.
Yeah.
So 1, 3, okay.
So you got 2 of them done so far. I do. I'm gonna do the third one. Are you labeling the points? This is what I end up with.
Looks pretty spidery.
Yeah, it looks like a spider. So when you go over the x-axis, you label it C, right? When you go over the y-axis, you label it B.
Swap them.
Yeah. It says.
Oh, nuts.
So copy the diagram, draw the other half of the graph so that the result is point symmetric about the origin, label that A. So that's down in quadrant 4. Then,
3, or 2.
no, it's in 4. Counterclockwise from upper right. So then, symmetric with respect to the y-axis is going to be B. So that will be in quadrant 1.
Which one is A?
The one in quadrant 4.
So the original.
The original one we aren't labeling,
Right.
according to this.
I got
So
it.
draw the other half of the diagram so the result is point symmetric about the origin. That's A. So that's down in quadrant 4.
I have my quadrants mixed up in my
Yeah,
head.
so do I.
Counterclockwise from the upper right hand. 1, 2, 3, 4. 1, 2, 3, 4.
Sorry,
So-
say that again. I thought it was.
What?
I thought it was 1, 2, 3, 4.
It's 1, 2, 3, 4.
I had it opposite.
Okay, so you started out with something that's like this,
I
right?
thought it was the other way.
Well, I feel like I
Well,
remember it that way because it's an order of where you're most likely to, which quadrants you're most likely to use.
When we get to trig, it'll make sense, okay?
Okay. I just had it backwards.
Everything makes a lot more sense when you get to trig. Okay, so then the first thing you're supposed to do is put it down here. That's A. And then you're supposed to bring it over, like this, and that's B. And then you're supposed to bring it over the x-axis, and that was gonna be translation C, reflection C.
Point symmetric about the origin. That just goes straight across. both.
Yeah,
You-
so when
X,
you,
flip the ball.
point symmetry about the origin means that you take the point and you figure out how far it is away from the origin and you take it that far in the opposite direction.
So you just basically flip X then Y, or Y then X.
Exactly, you switch both the X and the Y. Good observation, that's an important one here. So this down here, these are all negative X, negative Y.
Positive X for A?
These are, if these are X and Y, that is the opposite of X and the opposite of Y. I'm not saying that they're positive and negative values,
Oh, okay.
but I'm just saying that if these are the original, this image here is the opposite of X and the opposite of Y.
Sorry, I missed
Yeah, and what we did is we went about the origin. Okay, to get to here, we went over the y-axis, and xy turned into the opposite of x, and y stays the same. This is really important, this is a heavy lesson. This is your first real one, kinda. This, here, we go over the x-axis, so what did we change?
You changed your whole, Y
We
value.
changed the y to its opposite. So if we have that much straight right now, we're in great shape. So we're gonna build upon that. So we can, yeah,
So why wouldn't we label that in quadrant 2 as negative X, Y, and then in quadrant 1, X, Y?
you can do that too.
So it really is just based on your point of reference.
It's also, I feel like it's, right now to understand, these translations, in reference to the original image.
Here, if I
'Cause
map,
that's what the theorems say.
if I map xy onto negative x, negative y, that is said to be about the origin. However, let's get the other two first and come back and rename this one. If I map xy to the opposite of x and y, I take the opposite x value, so that must have been a reflection over the y. And if we map xy to x, the opposite of y, now we have to have gone over the x-axis. You gotta keep that straight. It's a little opposite thinking, but that's okay. It's kind of like x equals our vertical lines and y equals our horizontal lines. Okay, so now, if I look at this, let's say I map this over the y, and then I take that and I go over the x, and it will leave x the same and it will change y. Is that right?
Mm-hmm.
Okay, it leaves x the same and it changes y. So if I do this and I do this, I'm changing both the x and the y. So this is actually over both x and y axes. So to be a rotation. So when you take this and you bring it over there, and then you bring it down there, that's the same as just wheeling it around. All of those are analogous to one another, yes.
Is there, a specific name to reference that, purposeful of a rotation?
I don't know, there's use for it, but I'm not really sure
Just
exactly
wondering.
what you're asking.
Cause like, well, like, you could rotate that image about the origin and have it land anywhere, but to have it specifically land to where it's about the origin in the same location, that would be two translations, or two
Are you
reflections.
saying maybe you could just go part way as a rotation?
Right, so I'm wondering if this specific rotation that puts it in that location,
It's a 180-degree rotation.
oh, there's not like some special name for it, or just wondering.
It's a rotation about the, it's a reflection, a point reflection about the origin, or it's a rotation about the origin. And there's a reflection over the x and the y axis. I think that's about as far as we need to go with it. Okay, so there's three theorems. There's the symmetry over the y-axis. So when we see something which is Symmetric with respect to the y-axis. What they show us is that an example of that is like a parabola. There's symmetry over the y-axis, we've seen that, right? And for every point over here, which there is an x and a y, there is another point that that can be mapped to if we think of it as a reflection of half of the function. So if we take this much of the function and we reflect it over here, then it becomes negative x, y. At the same time, if you start on the left-hand side and you reflect it over, then these points map to x, y. Because just like I did here, that if that's x, it maps to the opposite of x when it comes over here. That is said to be an even function, which we'll come to in a bit. Then they give another function where if they take this, which is some type of an increasing function here, and actually the way they show it, they don't come out of here, they don't want to confuse you thinking, oh, well, that's going to be part of a parabola, but they start here, I think. And then what they do is they say, well, every point maps down here. So here, whatever is x and y up here as a point is going to map to the same x value, but the opposite y. Likewise, every y and x down here is going to map up there to the opposite value of y. So the negative 2 becomes a positive 2 and such. And those are what we end up calling odd functions eventually. No, my bad. That's not an odd function. No, we'll get back to that. The next one though, this would be an odd function here. And they use something that looks like y equals x to the third power. So if you come out and you take a point here, which is x, y, what this maps to is a reflection over the x as well as the y-axis, brings you down here. So now you have the opposite x. Instead of being positive, you go negative. And instead of y being positive, y becomes negative. So that's negative x. Slappy. Really slappy now. Negative x and negative y. At the same time, this down here maps to its opposites, which become positive x and positive y.
Oh, okay,
So that's symmetry about the origin. Symmetry about the origin, symmetry over the x-axis, symmetry over the y-axis. So, let's take a look at something. It says, prove that the graph of function of x, that's 1 over x squared plus 1, is symmetric with respect to the y-axis. Let me get rid of some of this. Right, and you get rid of this too, because you either wrote it down or you know where to find it, or none of the above. So the first example, prove the graph of square root plus 1 is symmetric with respect to the y-axis. So how do you prove that?
Does it have something to do with the exponent?
How would you go about proving it? Graph it. But the graph is not proof. Because just like one point that works in a function does not prove that the function works for all points, your graph is only a partial graph because of the idea of infinity for inputs. So what we need to do is we need to prove it algebraically. Okay, so when we go over the y-axis, what happens to xy? It
Maps
becomes
onto negative x.
negative
y.
xy. Okay, when we go over the x-axis, see, you guys should be writing some of this down, or else I'm sorry, I think you're gonna be
I've got
No, I've got it.
Okay, good. Maybe I'm just not watching, but this stuff you're gonna wanna be able to refer back to. When you go over the x-axis, xy is gonna map to negative x, y. And then when it is a rotation, it's
Wait,
over the x
It's
and the y.
negative yx. Over the x-axis, it's negative yx.
Oh, yes, you're right, I was right, I started going on. So here we go.
Test. Gotcha, Sheree.
Once I have them written down, there we go, okay. X and y, you have x, y, both of them are gonna change. Okay. So, if you look at this here, we are trying to prove with respect to the y-axis. And if it's with respect to the y-axis, that's this situation. So that means that every x value maps to y. And if we change the value of x to its opposite, it will map to the same y value. So in this case here, the function of x is equal to 1 over x squared plus 1, which is like saying y is equal to 1 over x squared plus 1. So if we think of it that way, we think of this as y is equal to 1 over x squared plus 1. This is the function. If I reflect it over the y-axis, every y value that I get from this function will be the same y value that I get if I substitute negative x into the equation. So, we substitute negative x for x. And we rewrite the function. So we take this and we plug it in there. And remember, we always have talked about the difference between parentheses in a quantity squared and no parentheses in a quantity squared?
Mm-hmm.
This is where the chickens come home to roost. If you don't have that straight, you go to early lunch. Sorry, I don't want anybody to go to early lunch, but that's how it is. You have to have that straight now. Okay, so what we get out of this is y will be equal to 1 over. Now, negative x has to get squared plus 1. Now I'm going to simplify the equation to prove this. This is just a proof. Y stays the same, 1 stays the same. Negative x squared is the same as having negative times a negative, and that's a positive. There's your proof. That's how you prove it. You'll be quizzed and you'll be tested on that repeatedly. Whenever it says prove, they're implying algebraic proof, not showing me. In Missouri, they say show me. That's why they call it the show me state. Here, this is prove it. Prove it to me. Huh?
For real? Or is it?
Yeah, Missouri's a show me state. It has to do with people way back when, well, show me. Yeah, something like that, that's all I know about it. Okay, so that's that. Now let's take a look at activity number 2. It's just the part of the graph of x, y equals 12 that is in quadrant 1 is shown. So, here's what they have. X, y is equal to 12. So this is all the combinations of numbers that multiply together to make 12. Okay, so I don't know if you can see where that comes from. Can you tell where that comes from? Can you tell where that function, what's the parent function of x, y equals 12?
Y equals x, or a divided by x plus b.
12 over x. So y equals 1 over x is the parent function. 1 over x, so how does 1 over x look when you graph it?
I saw it.
Stare at me, look back at me.
I saw it.
What is it?
It's in the first quadrant. It's 1 with 2.
Well, 1 over x graphs is a hyperbola.
Hyperbola, right.
So there's this down here too. So here's what they're doing. They're showing the part, it says the part of the graph that's in quadrant 1 is shown. Test to see if the equation is symmetric with respect to the y-axis, the x-axis, or the origin. So we got to figure out what it is. So if xy gives us a 12. So we have to check all three of these. So let's check the y-axis. So the y-axis check. What do we have to do? We take our x, y, and we change it to
Negative X.
negative x, negative y. So now we put in negative x times y is equal to 12. Well, in this case here, y is equal to 12 over x, right? Now this here, y would be equal to 12 over negative x. So we say no. Because we have to get the same thing back. If we don't get the same thing back, then it's not symmetric over. So this is not symmetric over the x-axis. In other words, I can't go and change the x value to a negative. Oh, I'm sorry, it's not symmetric over the y-axis. I can't change the x to a negative and then just flip it and put it over here. It's not over here. It doesn't happen.
It's not symmetric in any of them.
Well, we're gonna find out.
I mean,
So we start with x, y is equal to 12. We're gonna do an x-axis check. So now we wanna say x times negative y is equal to 12. And then we say, well, negative y is equal to 12 over x, y is equal to negative 12 over x, and the answer is no. Because we don't get the same thing back. So now what we wanna do is we wanna do a check of x, y is equal to 12. That's up there. And we wanna take our x and our y, and we wanna change it to negative x, negative y. So we have negative x times negative y is equal to 12. Now you wanna be pure. Negative 1 times x times negative 1 times y equals 12. Negative 1 times negative 1 times x times y equals 12. Negative times a negative is a positive. 12 xy is equal to 12. Y is equal to 12 over x. Yes. It is symmetric with respect to the origin. And that's why when you think of it, the parent function is y equals 1 over x, which graphs as a hyperbola in quadrants 1 and 3. Because they reflect back and forth. You can take part of a graph and make the rest of the graph. Just like what we did with the even function with the parabola, you can take part of the parabola and reflect it over the y-axis and get the rest of it. So if you could come up with a function for this thing here, you can reflect it any way you want. And it would map like this. So that's 2. So the definition of an even function. A function is an even function if and only if, for all values of x in its domain, the function of negative x is equal to the function of x. So in other words, the function of x gives me y. The function of negative x gives me y. Therefore, the function of x is equal to the function of negative x. So this is even right here. This is not. Because I have no definition for changing the x value. Doesn't work. This one here, if I change the x value to its negative, I don't get the same y out. Therefore, in this case here, f of x is not equal to f of negative x. Only here is it equal. Here it is not.
There it's equal to, function of x is equal to negative function x. As in negative being
Well,
outside of the f.
That one doesn't, yes,
That
sort
would
of.
be the odd function.
Well, an odd function, by definition, if and only if for all values of x in its domain, the function of the opposite of x is equal to the opposite function of x. Okay, so if we look at this here, you have the function of the opposite of x. So here's the function of the opposite of x has to be equal to, so here we don't have the opposite of x. Here we have the opposite of x. Let's check this one first. even though we said it's even, let's see if even and odd are the same, they shouldn't be. So if I take the function of the opposite of x, I should get the opposite of the function of x. And here the function of x is y, and the opposite of the function of y is going to be negative y, and that's not what I get. But this one here, if you take the opposite of x, so you take the function of the opposite of x, is it equal to the opposite of the function of x? And the function of x is y. So the opposite of y is negative y. So when you take a negative x, you get a negative y. Another way of writing this one here is for every, no, I won't say, I'm just going to leave it like that. Function of the opposite of x is equal to the opposite of the function of x. Here, and this is odd, for an even function, the function of x is equal to the function of the opposite of x. You plug in negative x, you get the same thing as if you plug in x. That's evens and odds.
And so what's the x-axis?
Neither.
Just mean,
So, when you say even and odd, is
Hold on. Let's ride on that one. You guys are, you're getting there with your understanding of mathematics, aren't you? Yeah?
yeah.
So your question, Haley, what about that one? Or what is that? Okay, so I take something and I do this, and I reflect it.
Yeah.
Is that an odd or an even function?
It's gonna be a neither function.
Is it a function?
No.
No, it's not a function.
Oh, yeah, because it's a straight line.
Neither.
So it's for undefined.
Doesn't work.
So from this, can we infer that, for all functions where the exponent on the x is an odd, it is an odd function, and when the exponent's an even number, it's an even function?
Yeah. Cubic, quintic, heptic, all are, 3, 5, 7, 9, they all graph up like that. Those are rotations about the origin. The opposite of it, if it was like that, they're all rotations. Yeah.
So even is just a word to describe where the graph is.
Yeah,
It doesn't actually mean.
no, it's an even function when it reflects over the y-axis for now. It's an odd function when it rotates about the origin for now. Or it reflects, point reflection over the origin,
So
which is both x and y.
there's nothing for the x-axis.
No, it's neither. If you have this situation going on, it's neither. Which means, I mean, you leave x the same and you get the opposite y. That's not a function. Doesn't work. All right, let's do some math. Now we're getting to places.
Now things are getting really exciting.
I think it is. Hey, you guys should be happier here this year instead of 4 years ago. 4 years ago, I didn't teach it very well.
We're here 4 years ago, and then I'd be going on my last year of college to graduate.
Where are you coming from?
All right, so
Income stuff.
here we have, these are our cheat notes here. It says we want to determine whether the function, of course they go and they write them different, mapping notation. 4x subtract 2x cubed, odd, even, or neither. If it appears to be even or odd, prove it. So the best thing to do is to try to prove that it isn't, or it is. And I think what we do, we should test it. That's the strategy that I would suggest. You could draw it
But the x
and then prove it algebraically. So if you draw that thing, what's it gonna look like?
It's gonna look like a
curvy boy.
Gonna look like a curvy
down
boy?
and then up and then down.
What's it do?
Down and then up and then
From
down.
the origin, where does it go?
Through the origin.
And then it goes which way?
And then it goes up
To the right.
into the first quadrant,
And then down again. Whee, like that.
yeah, all the way down,
Down,
into the
down,
fourth
all the way.
quadrant. Straight down.
Keeps going?
Straight down.
Well, similar.
Curve
Straighter.
down.
Oh, do they have it in the book?
Yeah, they do.
Oh, well, that'd go a long way, wouldn't it?
We're all just like pulling this out of our head.
Oh,
I was gonna say,
so it does this, it comes down, it goes up, and it comes down. Something like that. So, so do you think that that is a reflection over the y?
Yeah.
Yes.
No,
I
I
don't
think it's
see
a
it.
reflection
No,
about,
not
I think
You
it's
see a
about,
reflection over x?
I think it's about the origin.
It's,
It looks like it could be about the origin, not the way I drew it. It could be about the origin. So if it's about the origin, we should test that. That makes it an odd function. So we test whether it's odd or not. So what we do is we look at the function, f of x. That's the outcome. There's this is f of x right here, 4x minus 2x cubed. So this can be rewritten as such. So this is the function when x goes in. Now what we gotta do is we gotta put negative x in and see if we get the opposite of that. So we're gonna test odds. Okay, so f of negative x is equal to 4 times negative x minus 2 times negative x cubed. So now your algebraic skills will come in handy. So we better say that we have, this can just be turned into negative 4x, agree?
Mm-hmm.
What is this gonna turn into?
Plus 2x.
no,
Oh, yeah.
minus. It's cubed, so it's gonna
So
turn.
negative times a
Oh, yeah,
negative
so
times a
plus,
negative
plus.
is a negative x to the third times a negative. So that's what it becomes. So now I wanna ask myself, is that negative f of x? So over here, we'll move and we'll say that negative f of x is equal to a negative 4x minus 2x cubed. Remember back in Algebra 1 when we had to put a negative in front of the parentheses? And everybody struggled with that so much? So now this, negative f of x is equal to negative 4x. Negative times a negative is a positive 2x cubed. Is that this?
Yeah.
Yes.
Guys, it's an odd.
Odd. And that's algebraic proof because it doesn't matter what number you put in there for x. Any number by the rules of math will come out to an identical value. Is this with a negative in front of it?
so, I graphed that, it's not the same,
What did you graph?
both of them,
This?
both.
Well, sure, they're not the same. It's the opposite. It's an odd function. It should be a rotation.
I mean, I got a parabola and I got a squiggly. I could have.
Okay, I get, yeah. No? Yeah, you have squared. You change it to cube. When you saw the parabola, you showed it for the squared, right? You
What?
change that to a 3 and you got yourself a red on blue. Huh?
Seems actually,
Yeah,
got to debate mine.
okay.
Okay, we're good, never mind.
We're all good. Wahoo. All right, consider the function f with y equals f of x, 1 over x plus. Oh, gee, yikes. I'm gonna erase this, okay? It's fun when it all works, isn't it? It's not good. So we have big f of x is 1 over x plus 3 squared minus 7. What's the parent function?
K over x squared.
1 over x squared, yeah, we just put 1 in, there's no, the k is equal to 1.
And that one's supposed
Okay, so we have to consider this function, we have to give equations for the asymptotes of the graph. And describe any lines or points of symmetry. So, what kind of asymptote should we expect from the parent function? So y is equal to 1 over x squared, what does that look like?
1, and then plus 3 would be,
Isn't it
Let's stop, but
hyperbole?
just the parent function.
the parent function would be like
X-axis?
Yeah, it's like this, isn't it?
Both the x-axes.
Yeah, it's a reflection over the y. And a negative would just be down south, but this is all up on top of the x-axis. Okay, so if we rewrite this, y bring the 7 over x plus 3 quantity squared. Now we go back to our graph translation theorem. This is y subtract k x subtract h. So now the question is, what are the h and k's?
-7 and, negative,
What's h?
h is -3,
-3, and k is
-7.
-7. So that means that the origin moved to -3, -7. And so this origin moved to -3, -7.
So we're not an asymptote of -3.
No, I have an asymptote of -7.
Yes.
It's just moving it.
But we gotta be careful now. We need an x equals and we need a y
We have
equals.
both.
Okay, so the vertical
Yeah.
Because the other one has both.
asymptote, and then we have a horizontal asymptote. Okay, so the vertical is always gonna be written how? X or y equals?
X.
Vertical line is x. So,
-3.
what is it gonna be?
-3.
-3. And then the y will be
-7.
-7. You're welcome to graph and check, but that's how it works. I wouldn't graph it and look, if you can do this.
You would or wouldn't?
I would not. Because this is also what I'm trying to teach you and get you to learn our shifts like this. Just because we use them a lot this year, we do a lot of shifting. Where is shifting really gonna be handy? It's when we get to trig, and we shift trigonometric functions. You guys are in physics last year, right?
Mm-hmm.
Do you remember seeing, okay, so you have sine and cosine waves and stuff like that, right? But then you know how they get squeezed together?
Mm-hmm.
They get flattened out, they get made to look like this, they get made to look like that. Those are all shifts based upon this. Those are all shifts based upon this.
Are we gonna learn sine waves and stuff in this class?
That's trig, man, yeah. That's a third of what we do. You betcha. Yeah, then you'll start going, oh, now I know what they were talking about last year. So, properties of graphs of translation images, page 176. Look at that little blue box. Das ist alles. What's your sister doing, sitting at home watching soap opera?